Um, Happy Wednesday. Welcome back to class. We have attendance. If you go to Module 2, attendance 2, we just made it something for attendance. Just can go there and mention that you are in the class. The passcode is is 1955. Okay. So the passcode is 1955. Go and do your attendance. Okay, let's see what we're going to talk today. Are you able to do that? Good. Okay. So let's see what we covered last time. Last class, we were mostly talking about Moore's law, that showing how number of transistors in the chip increasing very fast. Every 2 years get like doubled. And so this gonna give us the idea, okay, so the computer is gonna get smaller, CPU is gonna get smaller and faster. And when they get smaller, you can have more transistors in the chip. So instead of having, for example, I don't know, 1 core, you can have 4 cores or more, or use more cache or other parts that can increase performance. Today we're going to talk more about that, how we can increase performance. And today we're going to see actually sometimes this Moore's law is not 100% working, because for a couple of decades the growing in actually performance was exponential, but it in some point it got the problem, and the problem was power, or the CPUs got so hot. That was because the number of transistors and increasing the clock is related to the power. We're going to see that today. And in that point, engineers like you guys realize we can't increase actually clock more than that. We need to stop there and think differently. Instead of having one CPU with a very high clock, we can have a lower clock but multiple CPU. We can do parallelism. We can do parallel things at the same time, doing multiple things, like with pipelining, with superscalar, with multi-core design. So today we're going to talk about that. We're going to talk about execution time. What is execution time? What is performance? What is relationship between execution time? Execution time means the time that you need to spend to run a task. And that's very related to performance, and how performance is related to actually clock. And also we're going to talk about how we can measure performance and what is power wall. We're going to talk about those things. First, let's define performance. So performance is related to a task, a program that you are running. If actually you can make it to execute faster, So it means you are increasing the performance. So if you spend less time to finish a task, so it's more performant. So the performance is inverse of execution time. So that's the formula that we have for performance. For example, if computer A finish a task in a half a time of computer B, we can say that a performance of A is 2 times more. So the things that I'm gonna emphasize is that performance related to actually a task, not the actually clock cycle of this processor. It depends, kind of, but is not directly related. So we can see in examples how that works. But this is the definition of performance, inverse of execution time. And how we can compare two systems. So easily we can actually compare that with dividing performance of, for example, computer A to computer B. We want to see, for example, how much computer A is faster. So this number showing, for example, the speed up computer A, if it is more than 1, it means computer A is faster. If it's less than 1, it means slower in terms of performance. So this is how we compare two computers. We can see examples soon. So generally speaking, for comparing systems, we need to see how long they take to complete a same task. So we have a same task, and we run that task in these two different systems, for example, and we see which one can run that task faster. So execution time is less. So and compute this formula to see which how much is the speed up. So if system A runs a program n times faster than system B, its performance is n times higher. So this is something obvious. Okay, so another thing, the text is already mentioned, lower execution time, higher performance. Execution time and performance are, inverse of each other. But what is CPU execution? What is execution time? Execution time is the time that is spent to finish a task. For example, you have a code and you want to see this code. You need to run this code in different systems to see which system can run that faster. So how compute execution time? Execution time actually depends on two parts. First, we need to see, for example, you have a program or task. This program has lots of lines, lots of instructions. When I'm talking about instruction, machine instructions. They have machine instructions, like, for example, I don't know, 1 billion instructions, not 10 power 9 instruction. But we need to see each instruction, how much this instruction actually, so computers have different clock per instructions. Okay, some computers need, for example, 2 clock per instruction. So each instruction spend 2 clocks, some 3, some 4. It depends the designing a computer, design the architecture, computer architecture. So we have that one. So that's called clock per instruction. So for example, clock per instruction for this is 2. And we have 10 power 9 instructions. So CPU clock gonna be 2 multiplied 10 power 9 clock. So this CPU clock cycle for a program can be computed based off this number of instructions multiplied by clock per instruction, how many clock each instruction needs. Okay, so to compute execution time, we need that one. Also, we need clock cycle time. We also have clock cycle time. What is clock cycle time? Clock cycle time is the time between two clock. So for example, is I don't know, like like a nanosecond, something. So we can see one example. So sometimes we are working with time. Here is time, clock cycle time. But if we give frequency, so most of computers working like frequency, like 2 gigahertz. So we are saying, okay, clock cycle for this computer is 2.5 gigahertz. So 2.5 gigahertz is frequency, is not time. We need to invert it to become time. Okay, so this gonna make another, any question about this? I want to erase it. We're gonna have one example and that's gonna clear that more. Okay, so this is just explaining what I wrote there. So clock per instruction, the CPU execution time is CPU clock cycle for a program as we computed, multiplied by clock cycle time. So, but if we have frequency, because most of the time we have frequency, frequency or clock rate is the inverse of clock time for sure. So we can write this as well. So this is another formula that most of the time we use this because we have computers like based off hertz, gigahertz, for example, based off clock rate, not clock time. Okay, so clock time and clock rate is inverse of each other, of course, because it's frequency and time. Okay, so this is how we can compute execution time. So execution time is coming from CPU clocks that one program needs multiplied by time of each clock, time of each actually cycle, or divide by clock rate. Okay, so let's have example. Imagine we have two computers. Computer A, imagine they are desktop computers, for example. This is computer A. And computer B is also desktop, but it has like a server one. This is computer A. The computer A has clock rate with like CR, clock rate 2 gigahertz. And computer B is 3 gigahertz, clock rate 3 gigahertz. Clock per instruction in computer A is 2, and clock per instruction here is 3. And we have one benchmark program. Benchmark program is a program that you want to check when you want to check two computers. You can use that code to check the performance. That benchmark is like a task they are doing. And this task is equal for both of them. So this task has 1 billion instruction, 10 power 9 instruction. Okay. We want to see which one is faster. Okay, we want to see which one is faster. To see which one is faster, what we need to compute? Performance, of course. We need to compute performance. Let's see how we compute performance. First, we need to find actually CPU cycles. CPU cycles, we need to see how many cycles this code need in this computer compared to this computer. They might be different. Why? Because clock per instruction here and there are not same. Clock per instruction is kind of computer architecture. How you can increase the clock per instruction. For example, if you use 2 cores, you can increase it. Or if you use pipelining, also is another way for make clock per instruction higher. Without changing the clock rate, you can still increase performance with increasing clock per instruction. So this is, in this example, we can see that. Okay. First, we want to see this code. How many CPU cycle we need for this core for this code in these 2 different architecture. For the first one is 1 billion instruction, 10 power 9 multiply 2. For the computer B is 3 time 10 power 9. So because so this is the number of instructions, and this is the clock that each instruction need in computer A and computer B. So we have this one, but we need to multiply that by actually a clock time, or divide that by clock rate. If we divide that by clock rate, we can find actually execution time. Execution time is CPU cycle. I don't need to clean it. So if we divide that by clock rate, because clock rates in these 2 computers are different. This is 2 gigahertz, that's 3 gigahertz. As you can see, even though this computer look faster, but execution times are equal. So when execution times are equal, means the performance are equal too, because performance is inverse of execution time. So again, they are equal. So these 2 computers are, kind of same performance, have same performance. Any question about this? Okay, so the main point is to find this execution time that coming from CPU cycles over clock rate. Clock rate is depend on clock, and CPU cycle depend on the code, depend on the task. Okay, so you can find that. Okay, so let's see how we can find this relative performance. This relative performance coming from, because performance is inverse of execution time, and we have execution time, but this execution time is 1. So it means these 2 are almost, they have similar performance. But imagine we want to change the system a little bit. We want to change the system B a little bit, like change the architecture. Like this computer was a B, and clock rate was 3. It was very good, very high clock rate. But clock per instruction was 3. For example, we use a parallelism method like pipelining or multiple core to decrease that, to shrink that to 2. Now we want to see how we're gonna find the speed up. how much we are increasing the performance in this change. So the only change that we did is clock per instruction. That, as I mentioned, clock per instruction doesn't need, technology. You are not changing, the size of, for example, gates or things. You just can use that using parallelism method that we can see in this class, like pipelining or multiple core systems. Okay, in this case, CPU cycle is going to be 2 times 10 power 9. 10 power 9 still is the size of this program. Benchmark that we mentioned is 10 power 9 is 1 billion instruction. And 2 is clock per instruction. So we have that. So we just need to multiply by 3, divide by 3 gigahertz. And 3 gigahertz is 10 power 9 hertz, because we want to find it in a second. So we need to change it to hertz. And when we divide that, it's going to be 0.67 seconds. From 1 second decrease to 67, 0.67. So to find a speed up, we need to find relative performance. Relative performance is what this time we want to check performance of B compared to A, and performance are inverse of execution time. Execution time with this is 0.67 second, and this is 1 second. So as you can see, we have 1.5. So it's like 50% increasing in performance. From 1, it becomes 1.5. So we just checked, we just changed clock per instruction, but a performance increase very good. Any question? Okay. But let's see. This is, again, let's go back to Moore's law. Okay, in Moore's law, the primary driver for performance was a scale of the chip, because Moore's law mentioned that, okay, we can exponentially increase the number of transistors inside the chip. So when we increase that, and the size becomes smaller and smaller every time. So the technology actually right now going from, for example, 350 nanometers move to, right now it's 10 nanometers. So 10 nanometers is we call that technology node, or transistor technology node, showing the smallest actually transistor. What is the size of that small transistor? It can be 10 nanometers now. And look at, from 350 nanometers shrink to 10 nanometers. It becomes like 30 times less. So 30 times less. So this is that technology change in these years. Based off the feature size is the smallest actually node that we can use. That is a transistor. It can be these nanometers. But when this is changing, how much the area changing? The area of the chip is kind of scaled like based off S square of feature size. When feature size changing like 30 times less, area scale gonna be decreased 30 multiplied 30 times. 900 times smaller. So that's very interesting, because the area, circuit area, is scaled with the square of feature size. It makes sense because this is a square. It is a 2-dimension. So it means you can make chips smaller, much smaller compared to before. And every 2 years, this becomes half based off Moore's law. Okay, so let's see what else we can get from there. So in terms of design, what we can do, we can have a smaller circuits, we can have a smaller chips, or we can have a still same size chips, but instead of having, for example, one core, we can have multiple core. We can have extra engineering part inside the chip. We can have more circuitry in the same area. We can have different things inside, like multiple chips for one of them. Or, for example, we can have bigger cache, because cache is very important in performance. Cache is very important because cache is very high-speed memory. And memory, because it's outside of CPU, is slow. Normally is slow. And but cache is, we have different level of cache. First of all, technology of cache is very higher. We can access to cache very faster, and we have different levels. Some level of cache are inside the CPU. Okay, and this hierarchy led us to access to this low performance memory faster, much faster. Okay, if you have bigger cache, that computer gonna work better, or more performance, higher performance. So in terms of design, so instead of having a smaller chip, we can have same size, but having more cache or multiple core. Instead of having one, have 2, 4, 16, sometimes 8, and even higher. Some computers using even higher. Okay, so what else? Also cost. Cost is also reduced when we can use a smaller dices for chips. We can decrease, we can shrink the cost, and we also can add more features, like same as the design part that as I mentioned. Okay, so what is the takeaway? So I want to say, okay, shrinking transistors is gonna it cause area. It's gonna decrease the cost, and it's gonna also increase the performance. But how much? It's gonna go forever. We can see in a couple of slides later that we need to, we are hitting a wall. When we go like that, we need to find some methods to because of power, because of the heat. We need kind of find another way to increase the performance without increasing the clock. This is what we're going to do. But right now, so far, based off the Moore's law, we have this characteristic. When we shrinking the size of transistors, we can get these advantages. Still, we have those. Regardless of clock, still we can use them. Okay? If we can find a way to not increase the clock, still we can increase the number of transistors inside the chip, but this can help us for parallelism, for doing things parallel, for having multi-core, or having more features, for more components inside the CPU that help us for performance later. Okay, so that's I already mentioned. But let's see what's happening with the clock rate. Okay, clock rate. In that example, we mentioned that performance is not directly clock rate, but is related to clock rate, because to find the number of clocks in the benchmark, you need to multiply that by clock rate. After finding that, we need to multiply that by clock rate to find performance, or divide by clock rate, clock time, or clock rate, and to find performance. So it's kind of related. And but clock rate is very related to power. So let's see how that works. First of all, increasing the clock rate is the easiest way for, if you want to increase the performance, like the easiest way is to increase the clock rate. Instead of having 2 gigahertz, for example, go to 3 gigahertz. Even some CPUs right now, maybe not anymore, but we had some CPUs working at 3 point something gigahertz. 3 point something is very high. But right now, most of the CPUs try to stay in lower clock rates, and they use multiple core to fix that. So that's the early trend. The trend was to just increase the clock rate. If you want to have higher performance, increase the clock rate. This was around 200 or 2000 or 2006. In those times, it was still processors that coming to the market, they were trying to have higher clock rate. And that makes sense. It's like normal things. If you have higher clock rate, you can have a higher performance. But some teams came up after that time. They realized when they are increasing the clock rate, the power becomes higher and higher. I mean, the CPU get hotter, and when it becomes higher than 100 watts, it's going to burn your hand even. You can't cool that down easily, or you need to spend lots of new technologies to cool the CPU down. Use like piping. I think in some advanced servers it still is used, but it's so expensive. Cooling that down is very expensive. So power increased actually with a square of voltage and clock frequency. Is actually a square of voltage, but yeah, we're going to see that the formula. So it means faster clock is more power, or more heat. And that's called power wall. So around 100 watts is too hot to manage. and this heat gonna limit the practical speed. So you can't go higher than that because it's get too hot. I remember that that time, like 2006, 2005. In that time, we were always worrying. It was two CPUs in the market, Intel and AMD, and everybody say, "Oh, AMD gets so hot, and you need to have very good." And we had like a big heat sink and fan inside the CPU in the old motherboards. If you look at those, they have very big CPUs. However, right now we have those for GPUs. Probably we have fans and heat sinks to make them cool, to not get the power wall. That's the point. Power wall is like a limit for designers, for engineers, for computer architectures. Okay, so that's called power wall, reaching to 100 watts, and we got that in like 2000, between 2000 2006. And cooling, as I mentioned, is the fans and heat sinks is limited. They can't do that. And advanced coolings are also exist right now. Even there is like pipe, and it's very expensive for using that. So what happened to industry? Industry were thinking, okay, what we need to do? So we need to find another way than increasing clock rate. So they stopped increasing the clock rate, and they found different methods. And this was the time that like parallelism or adding more cores actually introduced. Parallelism and adding cores or more core. That was industry response to that. Designers shift from adding frequency to parallelism, to adding more cores. Okay, so let's clean this up. So takes away is yeah, clock rate stop increasing because of power, and that is called power wall. If I ask you power walls, you need to know this one. Okay. Okay, we just have we have some information about the power trend and how we can, and why power increasing when we are changing frequency. So normally power consumption grows based on three factors. First is capacity load. Capacity load is like how many transistors are switching. This is a first capacity load. Second is frequency switch. So frequency showing how often they switch. So how many is load, how often they switch is frequency. And the last one that is actually more important is voltage, voltage that is actually squared. And when the voltage rise, power is actually like skyrockets. It's because it's squared, and it is increased a lot. You might ask me, okay, the voltage is kind of constant, isn't it, in CPUs? No, it's not. Voltage is changing in a when the performance changing, when you run more codes, for example, in your computer, sometimes you can notice that fans start working when you have multiple page open, multiple core running, a program that use lots of CPU resources. The fan start working because it gets warmer, it gets hotter. The voltage going up, the voltage is changing. So this voltage is not the voltage that used for gates like 1 and 0. It's not that. So the voltage is the power grows with the square of voltage, and also the frequency is also important. So as you can see, when you change the frequency, the power change, and voltage. And if you look at this diagram, this is showing what's happening exactly when you are increasing the clock rate. As you can see, clock rate increasing like 3.6 gigahertz is the maximum that they got that. But it reached the power wall because the power got 100.3. Power that CPU use is 100.3, so it's going to be too hot, need really cooling down. After that, this happened around 2006, 2005. These times happened. And after that, as you can see, they try to decrease this power, but they still try to keep the clock rate kind of same with different techniques that we might learn in this class, some of them. Another graph that is actually showing this trend is very nice. This graph is actually very good. As you can see here, the number of transistors is still following Moore's law. Till 2000, this is very new, 2020. As you can see, this is still growing. Maybe you say, oh, this is linear. No, because this is exponential. This part is exponential. So this is not linear. This is exponential, even though it's a line, but it's exponential. But as you can see, for a performance, for single thread performance, is not growing like linear, like as a line, coming here and become a little lower. And frequency, as you can see here, is not even going higher because of power wall. And watt also, as you can see here, is a stop, not going higher. But something increasing in 2006, as you can see, most of new computers start using multi-cores, using multiple cores. And you can see some of them even 10, even 100 cores. You can see some computers even using more than 100 cores. And this is actually very good diagram to showing them how this power wall affect the computers last few decades. Okay, so success versus failure was very related to this power wall in that time. So many computers, many CPUs got designed, but because of reaching power wall, they didn't go to market. And that was period that was very important to how we can have this actually conflict between clock speed and power wall. So and it give like a trade-off for engineers, because to increase performance, you should increase the clock cycle. At the same time, you not reach power limit. So all of these things came to the point that we need to find other methods than increasing clock cycle. And that's coming with multi-cores. As you can see, this is the like inside i7 CPU Intel. It has a big cache. As you can see, it has 4 cores. This is a big cache. Cache level 3, level 2, and level 1 are inside these cores. We have this level 3 is shared. We have the memory controller to connect to the memory, and we have MISC IO and PCI for connecting to the other components of the computer outside of CPU. So why multi-core emerge? Because when the clock rate limits by power and heat, Moore's law is still working. You still can have more transistors. What we do, we can add more cores inside. We can have more cache. And when you have more core, you don't need to have higher frequencies. You can do parallelism to increase, to get same performance. So multiple core per chip can execute in a parallel way. And industry shift to multi-core, some 2, 8-core, even 100-core, some CPUs. And clock stayed between 1 to 3 hertz maximum, and with the same cooling methods, without adding, different method of cooling. And right now, for improvement in computers, mostly they are doubling this, parallelism, or doubling the cores instead of increasing the clock rate. Okay, so that is the last one. And next class, we're going to talk more about performance, some new metrics for performance, talking about benchmarks and workload.